So this is the second part of metallic nanoparticles. In the first part, we've already talked about the synthesis method for achieving the metallic nanoparticles. Many type of uh, methods, chemical and physical methods, are already described. Now we're going to look at the properties of nanoparticles, metal nanoparticles, and also the applications of the metal nanoparticles. Let's start with the property of nanoparticles. As we know that when the bulk metal is reduced down to the cluster of metal or nanoparticle size of the metals, many properties are shifted and differ from the bulk metal. One of the properties that I want to mention first is the melting point, right? Because the size of the metal is smaller, we have higher surface area and we have higher surface energy. So it's easier for the metal to fuse up together, right? So the melting point or the fusing point of the metal is reduced down uh, because of the size of nanoparticles. The less size, the smaller size, the lower fusing points. In the graph here, showing the relationships between the diameters of nanoparticle in angstrom unit and the fusing point in Kelvin of the gold. So as you can see, a bulk gold has fusing point around 1300 Kelvin, but if the gold particles is reduced from the bulk into something smaller, like 100 nanometer, 100 angstrom, or to 50 angstrom. Let's look at the 50 angstrom here. The melting point, the fusing point, is just above 1000 Kelvin, and it can reduce down furthermore by reducing of the size of gold nanoparticles, right? So about 30 nanoparticles, 30 30 angstrom, the melting point is dropped to about 700 something, 800 Kelvin. And we can also make use of this kind of property. So what I'm showing you here is a kind of arts, a kind of handcrafted arts, right? The flowers made of some kind of clay. And this clay is rich of silver nanoparticles. So with a very high concentrated silver nanoparticles in maybe several tens of thousand ppm, we have a very sticky kind of mud-like silver nanoparticle. So we can use this kind of thing to have kind of piece of art like this. So mold them into petals of flowers and then combine them together, making a flowers thing like that. And we're gonna use the fusion point of the silver, which is now lowering down under 1000 Kelvin, to have these special applications. So with a very small cluster of silver nanoparticle here, with we fire the flowers here with the temperature higher than 600 degrees Celsius. So in less than 10 minutes, all the silver can then um, fuse together. And the stabilizers here is now calcined away. Because in this case, the silver is stabilized by a specific type of starch. So starch is a starch, right? Can be burnt away by a very high temperature like this, right? So left alone the silver, which is now fused together from nanoparticles into a solid silver, into bulk metal, bulk silver. So they fuse together, and at the end we have a flowers of silver. silver flowers, flowers. Right? So instead of using kind of silver fleet like like gold leaves, but this is the silver, right? And then using that as a starting point, making this kind of art piece of art, we use the silver clays instead, and then at the end we can easier, right, to make this kind of handcrafted piece of art, right? So this is one of the applications of the fusion point separation by reducing the diameter of the nanoparticles into very, very small, less than 10 nanometers. So another application is this one, which is called the conductive ink. So the ink is actually a very high concentrated small size of silver nanoparticles. So with a very small size silver nanoparticles dissolved into an ink, right, kind of ink, put it into a pen, then we can use it, draw a circuit lines, right? So instead of using silicon wafer and using kind of lead, right, and then fuse it with heat gun, very high temperature, we're using silver nanoparticles dissolved into water in high concentration, put it into a pen, so we can use it as an conductive ink. So we can draw lines, right, on the paper, on just a piece of paper. So we don't have to use a circuit board of the silicon wafer, thing like that. We use a paper, draw lines onto it, and then let the water or the solvent evaporated. We may use kind of rubbing, okay, to let it fuse together nicely, or just draw the lines and just leave it to be dried. So this dried composed of silver, which is a very, very good conductivity, right? Have electrical conductivity, very high electrical conductivity. Actually, it's the best conductor, electrical conductor in the world, in the universe, right? So we can use the silver nanoparticles in this kind of applications. After we draw the lines, then we can connect these lines with electrical cord to the batteries. So if we put the LED, right, between these two line of conductive ink, so as you can see, they illuminated, right, by the by electricity from the battery. So now we can use this electrical conductive ink to, instead of silicon wafer and the lead wire, we use this kind of thing instead. So everything seems to be more simple and easy with the conductive ink. This is another example and can be commercialized. Another very important properties of the metal nanoparticles are their optical properties. And the optical properties I mentioned earlier in the first half, that it is called surface plasmon resonance. Electron clouds of the nanoparticles bouncing on the surface of the nanoparticles when they interact with a specific wavelength or specific frequency of the electromagnetic radiation. The electrical field can interact with the bouncing of the electron clouds. So it depends on the size and shape and type of the metal of the nanoparticles. So here we have pictures of nanoparticles, solutions, colors, and the TEM image. So on the left hand of the first picture, it is the gold nanoparticles in spherical shape, right? And on the right hand is a gold nanoparticle solution on the very, in the fifth tube here, red color is gold nanoparticle. And then the left, far left tube, yellow color, this is the silver nanoparticle in spherical shape as well, with a similar size. So three of the solution in the middle is actually a solution, a colloidal solution of the alloy composed of silver and gold with different ratio. So with different ratio of silver and gold in the bimetallic nanoparticles here, uh, as you can see, they exhibit different colors, shaded from yellow to red, depends on the ratio of the silver and gold in the bimetallic nanoparticles here, or the alloyed nanoparticles. So as you can see, it depends on the types of metal here in the nanostructure. Next, in the middle row, on the left hand side, as you can see, this is the picture of the gold nanoparticles by TMMH. The gold nanoparticles here, instead of spherical shape, we have tubular shape, right, or cylindrical shape. The tubular shape, the tube of the gold, with different shape from spherical to the tubes. Now the electron clouds bouncing differently. So if the electron clouds bouncing differently, they absorbed different kind of electromagnetic radiation, resonate with different frequency of the electromagnetic radiation, induce the bouncing by different wavelengths of the visible light. So as a result, you can see here on the right hand, instead of red color, the tubular gold nanoparticle or cylindrical gold nanoparticle exhibit bluish color to green, green color, thing like that. And the color differed from one to another because of the ratio of the width and the length of the tubular shaped gold nanoparticle here. So they, with the different size of tube, right, different ratio of width and the length, the electron bouncing differently with different kind of frequency. So at the end, we have different colors of the tubular gold nanoparticles here on the right hand. And lastly, in the bottom lines, this is a prism or triangular shape of the silver nanoparticles, not the gold, but now silver nanoparticles. So normally the spherical silver nanoparticles appeared as yellow color, but in triangular shape, there are three corners, as you can see. So the bouncing of electron clouds are differ from the spherical without any corner. Like in spherical nanoparticles, there are no corners, but in triangle, we have three corners. So the electron density of the corners and in the central region are different. The bouncing of electrons, the movement of electrons are different, and obviously differ from the spherical one. So as a result, the electromagnetic radiation absorbed by these nanoparticles are different, right? So it varied from yellow color of a kind of triangular shaped nanoparticles to be red and to be blue and green color on the very end on the right hand. This depends on the ratio of the triangle, the size of the triangle, from the small one to the very huge one. So this is resulted, these are resulted from surface plasmon resonance, or SPR. Another example of the optical properties is from this Lycurgus cup. Lycurgus cup is a kind of cup, glass cup actually, crafted in Roman era, and this kind of glass was impaired by nanoparticles of gold and silver. Actually, the one who make this may not know really what is inside and what happened with his glass, why the glass can can be shined in different color when the light come from different direction. So if you look at the first picture of the Lycurgus cup here, it is like greenish color. So this green color, you can see this when the light shine from front, right? And if the light shine from behind, you can see the Lycurgus cup in red color. So as I mentioned, it is the surface plasmon resonance. So the electronic field interact with the electron clouds of the nanoparticles. So actually, if it is the spherical, it's not really matter. But if you can have like cylindrical or triangles, as you can see, so the dimensions is very important because the electromagnetic radiation, as you know, you have x, y, and z axis, right? So normally um, the magnetic field and electronic field, they are perpendicular with each other, and the light come from normally the normal light and polarized light are different, right? The polarized light is now filtered the normal light into just one kind of direction of the electronic field, right? So the electronic field, when it interacts with our nanoparticle, it also depends on the direction of the electronic field of electromagnetic radiation, whether it can interact with our nanoparticles better or not, right? So the direction of the light or the direction of the electronic field in electromagnetic radiation can alter the colors of the nanoparticles here inside. So from front, they may interact one particular way with our nanoparticle in the cup, and if it reflected from behind, it can then give you another kind of color, right? So this is like your cup, right? So there are many kind of handcrafted arts like this that exhibit colors from, I would say, reflections and what reflection. Um, I mean the different direction of the light reflected can give you different kind of colors. So all of these are resulted from the optical properties by surface plasmon resonance of the metal nanoparticles. So apart from this kind of properties, our metal nanoparticles can be applied into many fields in chemistry world. For example, many of the metal nanoparticles can be used as a catalyst. So if the metal can act as a catalyst, now we reduce down the metal from bulk, right, from bulk metal to be something smaller. We're increasing the surface area, so we're increasing the active site, right? So the catalytic properties of of the metal nanoparticles is very important, and there are so many applications out of the metal nanoparticles can catalyze so many kind of reaction, especially for the reduction. Right. Next, we can also use all these metal nanoparticles in biomedical applications as biosensors to detect some kind of diseases, or it can act as a kind of drug carriers. So it can then deliver the drugs into target organs, or it can control releasing of drugs, of some particular drugs, okay, in our body. And some of the nanoparticles can exhibit the antibacterial properties, antimicrobial properties out of them. So there are many possible applications. And for biomedical applications, we will talk about these kind of applications, including all other nanoparticles again in other lectures, okay, other video. But now I want to give you just some ideas about how we can make use of metal nanoparticles in this kind of application, starting from the catalyst. So there are many, um, so there are three different kind of methods. I would say kind of mechanisms for the catalytic pathway using our metal nanoparticles. First mechanisms is that the reaction takes place on top of the surface of the nanoparticles. So, as I mentioned earlier, the nanoparticles is very small, and the surface area is increasing drastically from bulk metal to nanoparticles. The smaller of the size, the higher surface area. So that means we have active sites, right? Higher active sites for the catalyst, the reaction, right? And the site or the phase of nanoparticles may be different from one facet to others because of the lattice orientation, right? We have, if you can remember the kind of crystal structure, right? So some of the crystal we have anisotropic effect. One particular phase maybe 111, another phase maybe 10 or 110, for example. So one particular phase may interact better with chemicals, right? So increase the number of the phase, increase the surface area is very important. So reducing down from bulk metal into nanoparticles can have more effectiveness of the catalytic properties of our metal, right? So this is the first mechanism. Reaction just takes place on top of the surface. Another method, another mechanism is catch and release. So actually, the catalytic species may be an atom of metal or a cluster of metal. So if the catalytic species of the reaction is cluster of metal, right? So our nanoparticles can act as a reservoir. So it releases some small cluster of the metals to catalyze the reaction. And after that, by metallic bonding, right, they recombine back to our nanoparticles. So this is a kind of equilibrium from releasing of the cluster and recombination of the cluster back to the nanoparticles. So with this kind of equilibrium, we can then release the cluster from the nanoparticles and then store it back to the nanoparticles, so our nanoparticle can act as a reservoir. This is the second mechanism. The last mechanism is the active species is our metal ion. So again, our nanoparticle can be a reservoir. So they release the metal ion, and now in solution we have metal ion, which is a kind of active species for catalytic cycle. But our metal ion may be not very stable. We can then modify it a bit by putting some kind of ligands or stabilizer to stabilize our metal ion and let the metal ion catalyze the reactions. So after that, the metal have has a proper reduction potentials. So they can be reduced by the environment, by the solvent or anything, and then returned back to our metal nanoparticle. So again, our metal nanoparticle is now act as a kind of reservoir, right? So these are three major mechanisms for catalytic cycles. So I want to give you one example of these applications using gold nanoparticles. So the gold nanoparticles here is treated with the sodium borohydride before using as a catalyst for conversion of nitro group to amino group. So now, after treatment with sodium borohydride, so the hydride ion interacts with our gold. So hydride ion containing 2 electrons, right? So with interaction with the gold, they just kind of dump electrons onto our gold surface. So now the gold is now condensed with the electron clouds on top of the surface. And then with very dense electron clouds here, our gold is act as an electron reservoir. So it can use this kind of electron in order to reduce the nitro group to be amino group. So our substrate is the para-nitrophenol. Now it's reduced to be para-aminophenol as the desired product. So this is how we can make use of our gold nanoparticles as a catalyst. Now we come to the biomedical applications, right, which is very useful. So the first application that I want to show you is using the gold nanoparticles as a colorimetric DNA detection. So let's say that we want to detect the DNA of a kind of disease. Let's say that it is leptospirosis or any kind of virus. So if we have DNA of the virus, target DNA of the virus, we know what is the DNA of the virus extracted, right? So now we can then design our gold nanoparticles to trap with these kind of DNA viruses. So with single-strand DNA or single-strand RNA maybe, we can design the complementary base series, right, and attach them onto the gold nanoparticles. So the DNA strands here, single-stranded DNA here, can, or maybe we can use PNA as well to increasing the affinity of the binding. So the DNA composed of very long chain of base pairing, right, and they can have steric effect, preventing the gold nanoparticles to be precipitated out, right, stabilize the gold nanoparticles. So DNA acts as a stabilizer. Not only by the steric effect, but also your DNA composed of several phosphate group, right, on the ladders. We have phosphate group. So the phosphate groups can act as a stabilizer as well by electrostatic repulsion, right, because negative charge of the phosphate. So here, the target DNA can be divided into 2 halves, the blue half on the left hand and the green half on the right hand. So we just design the complementary DNA strands specifically bounded with the blue and the red. So we put the complementary of the blue on one of the gold nanoparticles and the red half complementary of the red half to another gold nanoparticles. So after we mix these 2 types of gold nanoparticles together, so they're gonna trap the DNA by different halves, right? So the DNA here of the target DNA is now act as a glue to join our different type of gold nanoparticles together. So normally gold nanoparticles prepared in red color without the target DNA. Now, if we put the target DNA inside, we can detect the target DNA directly by our naked eye by just seeing the change of the color of gold nanoparticles. Because after we have gold nanoparticles and the target DNA, they combine themselves together. So at the end, we have aggregation of the gold nanoparticles. From individual nanoparticles, they gonna aggregate it to be clusters of gold nanoparticles. So gold nanoparticle itself is very huge, but now in cluster. So from nanometer scale, they may grow up into several hundreds nanometers, and at the end may be precipitate as a kind of micro scale particles or micro scale cluster. So if the nanoparticles is grow up like this by aggregations, now they can scatter the visible light, right? So if the nanoparticle cluster is in several hundred nanometer, which is in the region of the visible light, they can then scatter the visible light, and as a result, from red color nanoparticles solution or colloidal, we can see it as a kind of bluish color, right? This is because of the scattering of the cluster of gold nanoparticles. So now, by naked eye, we can see the target DNA, right? So we can make use of this by designing of the complementary base pair on the gold nanoparticles, things like that. This application actually depends on the temperature as well, because if the temperature is too high, right, higher than the critical temperature of the base pairing, we can cleave the particles back to the red color, things like that. So with lower color, it aggregated easily. Okay, this is one of the applications for biomedical purpose. Another applications for biomedical purpose is the antibacterial properties of the silver nanoparticles. I would say actually, the silver nanoparticles has no such kind of properties. The actual species for the antibacterial properties is the silver ion. So silver nanoparticles is act as a reservoir collecting the silver ion together in the nanoparticles, right? So the nanoparticles composed of several thousand of silver atoms. In solution, they kind of equilibrium, releasing the silver ion out. Okay, but because silver ion has quite a high reduction potential at plus 0.8, so they can reduce back automatically to the nanoparticle. So this is a kind of equilibrium properties. So in aqueous media, the silver ion can be released out and then recombined back to the nanoparticles. This silver ion is a kind of heavy metal ion, right? So they can interact strongly with some kind of proteins by coordinating nitrogen atoms on the proteins, electron pairs, nitrogen atoms to our silver ion. And this may denaturalize the proteins of bacteria and then kill the bacteria eventually. So the silver nanoparticles is now tested with 5 different kind of bacteria: the E. coli, S. aureus, MRSA, the Baumannii, and the P. aeruginosa, which these are quite a common bacteria found in almost everywhere in the world. So the concentration of silver nanoparticles is varied from 0 to 20 nanometer to 20 ppm, and then we can see the numbers of the cells, right? Survivals. So x-axis is the concentration of silver nanoparticles, and y-axis is the number of the bacterial cells. So what we can see from the pictures that all of the bacteria can be killed at the concentration of silver nanoparticles higher than 5 ppm. So this is quite useful. So that means if you have silver nanoparticles incorporated in any kind of materials, they can then slowly releasing the of silver ion, and that silver ion can act as an antibacteria, right? So keep everything clean, right? Free from bacteria. For example, if we incorporated these silver nanoparticles onto kind of fibers, cotton yarns, things like that, and we can then make kind of cloth with antibacterial properties out of silver nanoparticles, for example. And this is commercialized. One of the products that I want to talk about is the silver nanoparticle, is the silver nano incorporated in the detergents. So we have detergents, right? And now we just kind of mix the silver nanoparticles into the detergents. So these detergents using for washing of cloth and everything. So the cloth from washing machine uh, using this silver nanoparticles can act as a can we can kill the bacteria from the cloth as well. So this is very popular, right, products in Thailand, and this is how we make use of the nanoparticle of metal. So I want to end my talk with this picture taken by myself from Boston when I go to kind of a workshop there. So quite a colorful stained glass from a different type of metallic nanoparticles. Right? So it's quite uh, impressive. I really love the stained glass actually. So thank you for your attentions. Thank you very much indeed. And see you in other lectures. Thank you very much and goodbye.